We'll prove a weighted version of Cayley's tree theorem. So first of all, let's suppose we have n vertices. I'll draw 4 of them here. And let's suppose we have a tree connecting these labeled vertices. So for instance, one tree would be like this. Another tree could be this one. In other words, we'll be talking about spanning trees that visit every vertex at least once. I'll briefly refer to them as trees. And we want to associate a monomial to each tree. And the monomial consists of variables that we associate to each of the vertices. And then we raise them to the power of the number of edges that leave that vertex. So for instance, for the first drawing, we have x2 to the power 2 because the vertex is visited twice. If we label the second drawing, then the monomial associated to the second drawing will be x1, x2, x3, and x4 to the cube. So each tree has an associated monomial. So now suppose we sum over trees, particular spanning trees, we take the sum of each of those monomials for each tree. Then the theorem states that this is x1, x2 multiplied all the way to xn, x1, x2, xn to the power n minus 2. This is the theorem of Cayley weighted. So I call this Cayley's weighted tree theorem. And I learned it from some notes by Haiman. So how do we prove this? So first of all, note that the number of edges in a spanning tree will be n minus 1. And note that my definition here of my monomials is such that we can write this as a sum of products over edges in the trees, where the edges are denoted ij, and then I just multiply xi and xj. This is my definition of my polynomial, and therefore, because the number of edges is n minus 2 and each edge contributes 2 to the power of a monomial, the polynomial will be of order 2n minus 2. Which indeed is the case for the right-hand side. Now, the fact that the number of edges in a spanning tree is n minus 1 can be proven fairly easily recursively. So this we will not do. What we will do is we note that each of the monomials has at least one variable xi raised to the power 1. Indeed, since it is spanning our tree, therefore the power has to be larger or equal than 1. And then there must exist a leaf, namely a vertex where the tree ends, because otherwise I would have too many edges. So each tree has a leaf. So indeed, each of the monomials has at least one variable xi raised to the power 1. So by symmetry, let's assume that xi is xn, and we prove that each monomial contribution with xn to the power 1 agrees on the left and the right hand side of our equation. And then by symmetry between all the indices, we'll have proven our theorem. So let's see. So let's call this sum over trees of xt. We'll call it Cn of x1 to xn. Great. And what we want to study is Cn divided by xn, where we send xn to 0, because then we pick all of the terms which are monomials with xn to the power 0. So we have to prove that this is the right-hand side, which is x1 all the way up to the power x minus 1, where I've divided out xn, and then x1 plus x2 plus dot 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 plus xn minus 1, because I've put xn to 0 to the power n minus 2. So this I need to prove. Now, we'll do this by induction. So for instance, for n equal 2, we can easily verify the statement, even for n equal 1 actually, but for n equal 2 it's easy. And then we'll do this by induction, so proving it, assuming that this is true, that the theorem is true for n minus 1, and then proving it for n. So if it is true for n minus 1, then the previous expression is nothing but, so Cn over xn, for xn going to 0 is, well, x1 plus x2 plus dot 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 plus xn minus 1 times the sum over spanning trees with n minus 1 vertices in the variables x1, xn minus 1. This is by the induction hypothesis applied to the right-hand side. But then this means that Cn restricted to trees where xn is a leaf, we need to prove that that is equal to xn times x1 plus dot 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 plus xn minus 1 here times the sum over trees over n minus 1 vertices. So indeed, now if xn is a leaf, so if the nth vertex is a leaf, and I have a tree of n minus 1 vertices, then I can attach this nth vertex, I can attach it to all of the other vertices. I can choose the nth vertex will be a leaf, and what I need to add to my polynomial is, for instance, if I connect xn to x1, I need to add a factor of xn x1 to my monomial associated to this spanning tree. So indeed, we see that we can sum over n minus 1 over all the trees with n minus 1 vertices, and then multiply by xn times x1 plus xn times x2 plus dot 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 to get the sum over trees where xn is a leaf. With this, we have shown that Cn over xn, or xn goes to 0, is indeed x1, x minus 1, x1 plus dot 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 plus x n minus 1 to the power n minus 2. So this is now shown, and therefore we have proven the theorem by induction on n. So what does the theorem tell us? That the sum over all spanning trees of the monomials associated to the tree is nothing but this product times this sum to the power n minus 2. And this turns out to be a useful combinatorial theorem.